All right, guys, how are we doing today? Today we're going to cover internal forces, okay? We have three internal forces that we're going to be working on. We have normal force, which is axial loading, right? And that is going to be either tension or compression, right? And so we have a member here, okay? And it has forces exerted on it in the axial direction, right? Or along the same axes, right? Well, that is an axial loading condition, okay? That is some force, right? That is causing this member to be in compression, right? So this here is compression, and compression is negative, okay? Don't ask me why. That's just the way it is, okay? And then here we have another loading situation, and this here is a tensile loading condition. So that means that there are two forces that are pulling on this object, right? So this here is tension, and that there is positive, okay? Now if we take these members here and we split them in half, okay? We've done this with trusses, right? When we talk about compression and tension, okay? And we draw this left half of this beam here, okay? It has a force going to the right. It has to have an equal and opposite internal force going to the left, okay? We can also say that it's the same way this other way, okay? If we have a force going to the left, we have to have an equal and opposite force going to the right, okay? And we have talked about this in terms of trusses, because all of those forces are two-force members, right? They all have to be in either tension or compression. So we've talked about those members that are two-force members, right? So let's say this is F, H, G, right? Saying that, hey, this point up here is H, this point right here is G, this is also F, H, G, equal and opposite. But these are internal forces, right? This is a two-force member. Those are internal forces, okay? Both of these members, or both of these forces are pushing at the point, okay? Those internal forces are resisting some external loading condition, okay? So this here is in compression, just like this, okay? And the same exact thing for tension. But tension, we have our 2 points here, right? So let's say that this here is A and B. We have F, A, B, and we have F, A, B. So if the forces are pulling on these points, right, those there are in tension, and those are positive, okay? So now let's talk about shear. What is shear? Okay, I think of shear as scissors, okay? It means you have a bottom and a top, right? And when they cut, they actually pass each other, right? Go take a look at a pair of scissors. They do not cut like this. They actually slide past each other, making a shearing force. Now, what does that mean, a shearing force? Okay, let's think about a member again, right? Let's think about this member as having a force going up on it to the right, and then we have a force going down on it to the left, okay? That is exactly what we're talking about, our shear, just like our pair of scissors, okay? So this here is a positive shear, okay? And it gets its sign convention from the rotation that shear causes. That shear causes rotation in the clockwise direction, right? So it is clockwise shear, which is positive. That is positive sign convention, okay? And that's one of the big reasons why I do not want to use clockwise or counterclockwise to describe moments, okay? Because you'll find out here soon we're going to use clockwise and counterclockwise a lot of different ways, okay? We want to use right-hand rule to find our moments. Okay, so if we have clockwise shear that's positive, well, we have to have some negative value of shear, right? And that will be the exact opposite. Okay? If we have a shear here on the left going down, or a force here on the left going down, and a force here on the right going up, that there is counterclockwise shear. Okay? And that there is negative. Okay? Because that causes rotation in this direction. Okay? Don't ask me why, but that's the sign convention. Okay? Now, bending moment. Now, what do we talk about on a bending moment? Okay? So let's just take, oh, I apologize for bumping the camera. I'm terrible at that. Okay? So let's take this piece of paper here, or this packet of papers, right? And we see that this here is a straight beam, or in our case, it's a straight beam, right? And if we take this side, let me find it. Let's think about it this way, okay? And if we take my right hand and we cause a moment, right, or a rotation in this direction, we take the other side and do an equal and opposite moment, right? We see a deflection of that paper, okay? And that deflection of that paper is in a concave up direction, okay? So that means we have one moment on this side, we have another moment on this side, right? Equal and opposite, but it makes a concave up bending moment, okay? So like we said, we started off with our paper like this, okay? Well, if we introduce a moment in this direction, okay, and a moment in this direction, right, that will begin, or it'll want to deform our paper like this. Okay, does that make sense? If we grabbed this side and curled our hand, and we grabbed this side and curled our hand, right, we did that to both sides, we would get a concave up shape. And that there is positive, right? Okay. Now, the same exact thing happens if we do it the other way. Okay? So let's introduce a moment on this side in this direction. Okay? Let's introduce a moment on this side in this direction. Okay? Now, if we look at it, this one here is a negative moment from right-hand rule. This one here is a positive moment from right-hand rule. Okay? A way to think about this is all this moment is a force times a perpendicular distance, right? So let's say that we have this point here, we have this point A, okay? And let's substitute this moment with a force times perpendicular distance, okay? So if we want this to be a negative moment on this side, from A, let's move in this direction, okay, and apply a force in this direction, okay? Would that substitute this and say that there is this force this distance away, arbitrarily, right? That there will substitute this, okay? We can also say this moment over here, we want it to be positive from this point B, okay? So does that mean we can go in this direction and we can cause some force in this here times this distance, right? That's our perpendicular distance. This is our force, okay? That will substitute this moment. So it's like saying, let's pin both B and A and take our thumbs and push up like this, okay? Do you guys see how that there will cause a concave down? A concave down shape, okay? So either you can think about it as me grabbing this here and rotating like this, grabbing this, rotating like that to get a concave down shape, right? So if I grab this piece of paper and curve in this direction, grab this paper, curve in that direction, right? We get the concave down. Okay, it's also like saying I'm gonna grab the corner of this paper with this hand, take my thumb and push up in the center. Do the same thing. Grab this paper here and push up in the center, right? That's the force times perpendicular distance, okay? And that causes this bending moment down, okay? And that there is a negative, okay? So I think of a smiley face, right, as positive. I think of a frowny face as negative. Why frown, right? Life's too short. All right, so this here covers sign convention. Okay, I hope you guys, I hope you guys don't have any questions, but we could go over, which I think is important, what is the terminology of these and what is the units, okay? So let's think of a beam, right? And the beam is attached to the wall, okay? Okay, we think of this joint or this connection to the wall here as a support reaction, okay? Let's say this point here is A. Okay, let's analyze this point. Okay, what support reactions do we have? If I grab this beam and try translating it to the right, can I? No. Why? Because there's some force here in this x direction, AX, that resists that motion. Okay, there's also some force here in the Y resisting the translation. Okay, now if I grab this beam, right, can I rotate it about A? No, I cannot. So there's also some moment about A. Okay, I hope you guys all see that. Okay, there's some force in the X, stopping translation in the X, right? F is equal to ma. If we want to talk about the X direction, we say acceleration in the X direction, right, has to have some force in the X direction. Okay, this is statics. Acceleration is 0. It cannot move. Why can it not move if there are forces in the X? Because there's also some forces canceling it out, right? Because this is the sum of the forces in the X. Okay, that's statics. Okay, and that's the same thing with moments. Sum of the moments, right, are equal to I bar alpha. Okay, now if we're talking about alpha, we have to also denote a direction, right? And that's rotational acceleration about some axes, right? So let's use X again, right? Rotational acceleration about the X axes, right, cannot happen in statics. It's 0 because the sum of the moments about the X axes have to also be 0. Okay, they have to cancel each other out. All right, so now where does this come into internal forces? So let's say that we want to cut this beam, all right? We want to cut this beam right here, okay? There's other stuff going on over here. We don't really know what's going on, but let's just say we cut it. So our forces stay the same on this side. We still have AX, we still have the moment of A, and we still have some AY, okay? And we still have this portion of the beam here, okay? But over here, what do we have? We have some force that has to be in this X, right? Why does it have to be in the X? Because it has to cancel that out, okay? What about in the Y? We have to have some force in the Y, right? That has to cancel out that Y, okay? And if we have a moment, which is a positive moment, right? We have to have a negative moment in this direction, okay? Does that make sense? If we have it over here, it has to be over here to cancel it out, okay? Now, what do we call these over here, okay? So this axial force here, right, is our normal force, right? And it is considered axial because it acts along this axis, right? And that there is denoted as N, right? Normal force, which has the units of forces, right? So in this case, let's just say that we're in the SI units, and we're going to say that it is in newtons, okay? I hope you guys all get that. Okay. So if that there is an axial force in newtons, what do we have for shear? Okay. So let's look here. We have our AY. We have this other Y component force, right? And we see that there's a force up and a force down, right? So that there is shear. Now, what do we call shear in terms of variables? That is V, right? And that is also a force. So in the SI case, that would also be newtons. Okay? Now we have this moment, right? And this moment, okay? and that stays just a moment, but we can say, hey, maybe it's a bending moment, right? That might be good to know, okay? And that there is still in newtons times perpendicular distance, which is meters, okay? If we're in the SI units. Okay, I hope we all get that. Okay, so let's go over an example. And for the people that are in my tutoring session, they have seen this example a lot. Okay. So we're going to have a beam, and that beam is going to be attached to the wall. Okay. And then it's going to come to a point here, and it's going to come down, right? And off of this, it is going to have a roller. And that roller is going to be sitting on a wall. Okay. Over here, we have a distributed load. Okay. And that distributed load acts like this. Okay. And then this here also has a distributed load. Okay, this distributed load here is 200 newtons per meter. Okay, and this one here is 400 newtons per meter. Okay, this here is 3 meters. This here is 3 meters. Okay, now this overall distance over here is 4 meters. Okay, this point here is point A. This point here is point C. This point here is point D. Okay, and this point here right in the center is point B. Okay, maybe let's write that B over here. Okay, now let's talk about a problem statement. Okay, it wants us to find the internal forces at B. So it wants us to find NB. It wants us to find VB. And it wants us to find MB. Right? So it wants us to find the axial loading condition at B. It wants us to find the shear loading condition at B. And it wants us to find the moment condition at B. Okay? And that is here at point B. So now we have our overall beam, right? So now what's the first thing we need to do to solve a problem like this? Well, it's just like everything else, right? We either need to simplify or we need to find support reactions. Okay? So let's do both at the same time, right? We have 200 newtons per meter over 6 meters. Okay? So that there, distributed load, will be 1,200 newtons, right? 200 newtons times 6 meters is 1,200 newtons. Okay, we also have this 400 newtons per meter, right? And that there acts right here over 4 meters. So that here is 1,600 newtons, right? Maybe what we'll do is say over here is 400 newtons per meter, and we'll say right here is 1,600 newtons. Okay? So that was simplification. I agree. That should be a good place to start. Now let's put in our support or our external forces, right? So we have 2 of them solved for, or simplified. Now let's look at support reactions. Okay, we have 2 support reactions here. We have D and we have A. D is a roller, right? And we're gonna do it like we do everything else. We're gonna grab this beam, and we're gonna manipulate it and figure out how we can solve for it. Okay. So if we take D, point D, right, or we take this beam attached to point D, can we translate that in the y direction? And we say, yes, we can, right? It just rolls right along in the y direction, okay? can I take this point D and translate it away from the paper? Well, we're like, yeah, just think of it as a skateboard. Can I lift the skateboard off the ground? Well, of course I can. Okay. Can I push the skateboard into the ground? No, I cannot, right? So we know for a fact that there is some support reaction here, which is dx, right? If we come up here and we say, hey, this is the y, this is the x, right? In this x direction, dx has to be going to the right. That's the only way that that support reaction will work. Okay, now we gotta look at A. Okay, so A is a fixed support. Well, let's just say this is A. Is a fixed support, right? It's welded to the wall. So we're gonna do the same thing. Can I translate this beam away from the wall? You're like, no, it's welded, right? It's fixed. So there has to be some force in this x direction. There has to be some force AX. Do we know the direction of AX? No, we have no idea. So if we have no idea, we should just assume our positive x sign convention, right? What about in the y? Can I translate A up and down in the y? No. That there is some AY. Okay? Do I have any idea the loading condition? I was like, well, I don't know. A lot of this is going down, so let's assume it's up. I don't know. Just a quick thought, right? Sorry, I keep hitting my camera. All right. And what about, can I rotate this about A? If I grab this beam, can I rotate it about A? No, I cannot. So there's also some moment about A, right? And I have no idea the direction of this moment, so let's assume it's positive. If I say right-hand rule is positive, that there is a positive moment. Okay. So now where do we start something like this, right? We want to find NB, VB, and MB, right? So let's just think about this point here, okay? We need to find those internal forces. And like we talked about earlier, the way that we thought about it is if we have a point here, which is B, okay? We need some NB, we need some MB, and we need some VB, okay? Now, does this sign convention match? Well, let's look. We have some AX, we have some AY, and we have some MA, okay? Now, do we know anything about these? No, all of these are assumptions, right? So we can't say anything about them, okay? But this is how most professors start by thinking about things, okay? And that's not the only way to think about it, as we'll see here, okay? So if we were to solve for these, right, we just need to find support reactions, okay? So I don't think we should split this up right away, because look at that, right there, 6 variables. We don't know any of them. We cannot solve for that. So let's look at what we have, okay? This here is a support reaction attached to the wall, 3 unknowns. Over here, we have a roller, which is the 4th unknown, okay? We have 4 unknowns, 3 equations. Can we solve them? The answer is no. So where the heck do we start? Okay. Well, what I did not give you in the problem statement was this here is a frame. Okay. And now what does that mean for us? Well, if we go back to the last exam, we think about frames and machines. What's the big thing about frames and machines? If there's a pin, let's take it apart, right? So there's a pin right here at C. Okay. So let's take apart this beam. Okay, if we were to take it apart, that just means we can cover up one side of this, right? And analyze the pin as well as this roller, right? And this beam, okay? We could also analyze these 3 and this. So what we'll do is we'll just draw it. We'll draw both sides, okay? Let's start with the overall beam, okay? We say that this beam, okay, looks like this. It has this distributed load. Okay, it has some AX, it has some AY, and it has some moment about A. All right? Okay, and at this point C, we've taken apart a pin. okay? So what we're gonna do is go back up to here and analyze this pin, okay? If I grabbed this member right here from C to D, if I grab it, can I translate it to the right? No, I cannot. So there is some CX, okay? Can I lift or lower CD? No, I cannot. So there is some CY, okay? And we've drawn a free body diagram for this here. So now let's draw another free body diagram that goes from C to D, right? This here is point D. It has its distributed load. Okay. And if we analyze this pin here, okay, now what we're going to do is we're going to forget about this part, and we're going to analyze if we grabbed here. If we grabbed here, can we lift or lower this, right? And we only think about C. We forget about D, right? We take that out of the equation. Say that this is a fixed support, right? If I lift this beam, okay, I can't. Why? Because there's some force in the Y from CY. Okay, so when I go to draw it, there's some force here. But in what direction? Okay, these two forces have to be equal and opposite. Okay, so this CY has to be down. Why? Because it has to be equal and opposite of that. Okay, now CX, if I fix this and I try moving this here, okay, can it? No, it cannot move in the X direction. Okay, so that there is some force in the X. And it has to be to the left because up here is to the right. Okay, these 2 points have to be equal and opposite. Okay, so what I'm gonna do is move the CY over there. Hopefully it's a little bit clearer. Okay, and it is down. Okay, the CY is up. The CX is to the right. The CX is to the left. Okay, and that's how we have to think about this. Well, now what do? We still have 1, 2, 3, 4, 5, 6, 7, and we have this dx to the right. We have 8 unknowns. So what do? We pick the point which has the least unknowns. Which of these two members has least unknowns? That is going to be this portion right here. Okay? This is where we're going to start. So what we're going to do is say, all right, let's do sum of the forces in the y, which equal to 0, which are equal to, what do we got? All we have is this cy. So that says that cy is equal to 0, right? If we say, hey, up is like that, negative cy is 0, right? All right. So now let's do sum of the forces in the x. Okay, what do we got? Okay, well, we have this distributed load, which is simplified into 1,600 newtons, right? And if 1,600 newtons is going to the left, well, that's negative 1,600, right? And we said plus dx, right? Minus cx. Okay? Did we solve anything? No, we have an equation here with two variables. So was there a way that was smarter to start this? Well, I think if we took some of the moments about C, that would be a smart place. Okay, why? If I took some of the moments about C right here, I could get two of those variables out of that equation. The only part of that equation, or the only variable in that equation, would be dx. Okay, so that would be a good place to start. What if I took the moment about D? Would that help me any? Well, dx acts through that, but so does cy. See how its line of action acts right through D, right? So either of those two places would be a great place to start. So some of the moments saying, hey, right-hand rule is positive, is equal to 0, which is equal to, we have this dx here. dx, right, times 4 meters, because that's this distance here, okay? And this here is positive. Why is it positive? Because if we put our thumb through the positive z-axis at C, lay our hand across perpendicular distance, right, which is this 4 meters, curl our fingers in the direction of that force that is a positive, right, moment, minus 1600, okay? Now, what is its perpendicular distance? Well, we know that this distributed load is uniform, right? It's a rectangle. So we can say that that distributed load acts right through the center, right? And that would be 2 meters, right? So we can say that dx is equal to, okay, so dx is equal to 800 newtons. I believe my mental math is correct. Yeah, dx is equal to 800 newtons. Okay, hope you guys are all getting this. Sorry I didn't fill in this diagram down here with the same measurements and stuff like that, but I hope you guys all got dx is equal to 800 newtons. Okay, so now we can go back to this equation here, sum of the forces in the x. Okay, let's just rewrite it. Sum of forces in the x are equal to 0, which are equal to negative 1600 newtons. Why is it negative? Because it's acting to the left. Okay, plus dx minus cx. Okay, dx is 800, so we have negative 1600 plus 800 minus cx, okay, is equal to 0. Okay, this here is 800, or is negative 800. So then cx is equal to negative 800. Okay, now what does that mean to us? Negative 800 newtons. Okay, if cx is negative, that means it's in the wrong direction. Okay, now would that make sense? If we have dx this way, and it's 800, right? We have 1600 to the left, okay? Cx has to be back to the right to give it back that other 800. Okay, so we're gonna switch the signs of our drawing, or switch the arrow of our drawing, okay? And when we do that, we have to go back and change our equations, okay? We have negative 1600, because it's going to the left, plus dx, which is going to the right, now plus cx, okay? We have to change that, okay? Now we go back to this equation, it's plus cx. Now this equation here is a positive 800. Okay, now what does this mean? That means we've assumed correctly. All right, why is it important to change our drawings? Because this drawing, cx is now proven to be to the right. That makes this cx in this diagram, it means it has to go to the left. It is now proven because these have to be equal and opposite, right? And that's all equilibrium equations do for us, is they prove the directions and the magnitudes of our forces. Okay? So now, for this member right here, let's do sum of the forces in the y. Oh, sum of the forces of the y I already done, right? Cy is 0. So this here is 0. This here is 0. Okay. So now, let's draw one more time our horizontal beam. Okay? We say that we have this beam here. It starts at A. Okay, and it goes to C. We have a distributed load, which actually it's horizontal. I'm sorry. Okay, it's horizontal. Okay, it is 200 newtons per meter over 3 meters, right? So combined, it is 1,200 newtons, right? And from our diagram up above, we know, hey, this CX acts to the left. So in this diagram, we're going to say, hey, CX acts to the left, and it is equal to 800 newtons. Okay. Over here, we still do not know AX. We still do not know AY, and we still do not know moment about A, right? Those are all just positive assumptions. We don't know. Okay. Now let's go back to our problem statement of what we want to find. We want to find N at B, V at B, and we want to find M at B, right? So we want to find the normal force, the shear, and the moment at B. Okay? So over here, we're just going to write a little answer box. NB, VB, and MB. Okay? All right. So right here is the point B. Okay, so what do we know for variables, right? All we know is CX. But we just said earlier, like, this is what we need to find. So if we wanted to find this, we need to find AY, AX, and MA, right? Well, in this case, not so much. Let's just look at the part of the beam where we have the most information, okay? Right here on this right-hand side of the beam, we have the most information. So why solve over here to then solve here? Why can't we just split the beam right now? Well, I don't know. Let's just try and find out, right? Okay. So if we started drawing the beam from B to C, okay, and we draw in our distributed load, okay, and that's 200 newtons per meter, okay, over 3 meters. Okay, we do not account for the 1200 newtons, which was our distributed load before. Okay, hope that makes sense to everybody. All right, sorry, I had to plug in the phone real quick. All right, so we have this 200 newtons per meter over 3 meters. So that here comes into its own distributed load, right? And that there is 600 newtons, okay? Acting at 1.5 meters, right? We know that it's uniform, right? Because it's a rectangle, so it'll act halfway in between, okay? But over here at C, we have to give our known information, okay? And what is our known information at point C? Well, all we have is this CX, which is equal to 800 newtons. But over here, if we split this beam here, well, what do we have over here? Every time we split a beam and think about internal forces, we have to think about our N. We have to think about our M, okay? And we have to think about our V, okay? And in this case, do we know any of the directions of these? No, those are all assumptions, okay? But if we were to look carefully, hey, this N has to be opposite of this here, right? This V has to be opposite of this here, right? And this M has to be opposite of all the moments happening over there. So let's see if we can solve for these. Why don't we just start with our 3 equations? Sum of the forces in the x are equal to 0. And we're going to note to the right is positive, okay? Which is equal to, well, we have N, which is going to the right, minus 800, because it's going to the left. Anything else in the x? Nope. So our N is equal to 800, okay? But we talked about it earlier, right? We talked about sign convention for N, right? And we said, hey, sign convention comes from tension or compression. So is this in tension or compression? Okay, so let's look at our member, right? BC, right? Are we pushing on that member or are we pulling on it? Or just think about the points. Are we pushing on that point or are we pulling on that point? All right, so we are pushing on that point. So that is newtons in compression, right? And we said that compression is negative, and we give sign convention right here, right? We never throw a negative out front. We put it with our understanding of what's going on. Sign convention is tough, okay? This class especially, okay? So NB, right, is what we just found, is equal to 800 newtons in compression, which is negative. Okay? Now, let's do sum of the forces in the y. Which equal to 0, which are equal to, we have V, which is positive, minus 600 newtons. Okay, and that's all we have because there is no Cy. You guys see that? Okay, so V is equal to 600 newtons. Okay, now what is our sign convention for this? Well, first off, did this equilibrium equation give us a positive or negative value? Well, it gave us a positive value. So what does that mean to us? That we assume correctly, right? This does not say that this is positive shear. Okay, we have to give it its own sign convention. Well, so let's think about it. If we have shear going up like this and this force going down like this, right? Well, think about what rotation does it have? Well, let's just say it's clockwise. Okay, that is clockwise shear. What does that mean? It means that it's positive, right? If we go back to our sign convention, we said that clockwise shear is positive. Okay? So we can put that down here. V of B, shear of B, is equal to 600 newtons clockwise, which is positive. All right? Now moments, right? We need to find this M of B. What is that? Well, let's do sum of the forces. Okay, denoting that right-hand rule is positive. Sum of the moments about B are equal to 0, which are equal to, all right, well, we have this force here, 600 newtons, times 1.5, right? What else we got? That's nothing, right? Cx won't show up in the equation. Why? Because the line of action acts right through that point. So all we have is 600 times 1.5, right? But we also have to include this MB plus MB, right? So what about sign convention? Is MB positive? Well, yeah. From right-hand rule, that's positive. What about this here? 600 times 1.5. Put a thumb along the perpendicular axis, lay our hand across this perpendicular distance, right? And curl our fingers in the direction of that force. That shows us that this here is negative. So MB is equal to 900 newtons, okay? And how do we say sign convention for this? I always just say, hey, it's our frowny face, and I put a negative, right? Or I can say concave down negative, okay? And this is how I did it on the exam, concave down negative, okay? But I also threw that in there, because why not? It's pretty cool, right? So 900, and this is Newton times meters, I apologize. Newton times meters, and I put like this negative. And I said concave down in the answer box. Okay? So I want you guys to see that this stuff, positive, negative, never comes from an equilibrium equation. Okay? And what we want to do is we want to start from the most knowns and work towards what we want. All right. Y'all have a good one. Stay safe.